The next section we're going to talk about is section 4.1. This is about scatter diagrams and correlation. And here, instead of talking about qualitative data, we're talking about quantitative data. And again, we're looking at a relationship between two variables. The objective that we're going to talk about is to draw and interpret scatter diagrams. A scatter diagram, you can also call this a scatter plot, is a graph that shows the relationship between two quantitative variables measured on the same individual. So each individual in the data set is represented by a point in the scatter plot. The explanatory variable is plotted on the horizontal axis. The response variable is plotted on the vertical axis. And once we have all the data points plotted, we can look at the resulting picture and get an idea whether the variables are related or not. So linearly related, then we say that they're positively associated if whenever the value of one variable increases, the value of the other variable also increases. And negatively associated if whenever the value of one variable increases, the value of the other variable decreases. So we'll look at some pictures here. In this first picture on the left, we would say that this scatter plot shows a linear relationship. A linear relationship basically means that we can see some type of a straight line pattern. And this would be positively associated because as our explanatory variable increases, our response variable also increases. In other words, our straight line pattern is going up as you go from left to right. In this graph on the right side, again, we can see somewhat of a straight line pattern, but it's going down as we go from left to right. So this would still show a linear relationship, but the two variables would be negatively associated. Now, some other types of relationships we can see from scatter diagrams. In this one, it looks like there's a relationship, but it's not linear. It doesn't have a straight line pattern. This one also shows some type of relationship, but it would not be a linear one because this is not a straight line pattern. And in this last one on the right, there doesn't seem to be any relationship between the variables, linear or not. Now, if we're just looking at linear relations, then we have some further breakdowns of what type of relations we can have. This one would have a perfect positive linear relation. These points are exactly in a straight line, which gives us a perfect linear relationship, and the line is going up as we go from left to right, so that makes it positive. So this would be a perfect positive association. Now these two would also both be linear relationships and positive linear relationships. This one would be a fairly strong linear relationship because the straight line pattern is fairly obvious. In this one, the data points are much more spread out and the straight line pattern is not as strong, so we would call this a moderate positive linear relation. Here are the other types of linear relationships we can have. This one, again, since we have a perfect straight line pattern, but it's going down from left to right, this would be a perfect negative linear relation. And then here we have a strong negative linear relation because the straight line pattern is still fairly obvious. And in this one, the straight line pattern is quite a bit harder to see So this would be a moderate negative linear relation. Let's look at an example of scatter plots. The data shown in this table is based on a study for drilling rock. The researchers wanted to determine whether the time it takes to dry drill a distance of 5 feet in rock increases with the depth at which the drilling begins. So depth at which drilling begins is the explanatory variable, x, and the time in minutes to drill 5 feet is the response variable, y. We're going to draw a scatter diagram of the data and then comment on the association between the two variables. Here's our data again, and here's our scatter plot. So notice again that each one of these rows in our data table becomes a point on this graph. So if we look at this first one, our x is 35 and our y is 5.88. So all we're doing here is plotting points, just like you would have done in an algebra class. So this point would be 35 for the x. For this point we'd have 35 for the x and 5.88 for the y, and so on. Each one of these points on the graph represents one of these rows on the table. Now, looking at our scatter plot, there's not a strong straight line pattern here, but it does appear that in general the data points go up as we go from left to right. And it's somewhat of a straight line pattern. So we would say that our two variables are linear related with a moderate positive association.
Another way to determine the strength of a linear relationship is by looking at the linear correlation coefficient. The linear correlation coefficient, R, measures the strength of a linear relationship between two variables in a data set. So the number R is actually calculated from the values in the data. But for right now, we're not going to look at actually calculating it. We're just going to look at the relationship between R and the scatter plot. So the possible values of R are anything between -1 and +1. A negative value of R indicates a negative relationship between the two variables. A positive value indicates a positive relationship. The closer R is to 0, the weaker the linear relationship is. To get an idea of how R helps us determine the strength of the relationship, we can look at R values for a data set with approximately 20 data points. So for a data set like this, an R value between -0.7 and +0.7 indicates a weak relationship or no linear relationship. An R value between -0.7 and -0.9, or between 0.7 and 0.9, indicates a moderate linear relationship. And a value between -0.9 and -1, or between 0.9 and 1, indicates a strong linear relationship. And again, the closer R is to either -1 or +1, the stronger the relationship is. Let's look at some scatter plots and look at the R values that go with them. Here's a scatter plot we looked at before. This is a perfect positive linear relationship. So the R value for this would be +1. This one is a perfect negative linear relationship because it's absolutely in a straight line. So the R value for that is -1. Now in this scatter plot, there is no relationship at all. So the R value for this would actually be 0. So if the R value is 0 or close to 0, then we just say there's no relationship. For this scatter plot, we can see that the data is going down as it goes from left to right. So this would have a negative relationship. And we can see that there's somewhat of a straight line pattern. The R value for this data is actually negative 0.846. Remember, the negative indicates the negative relationship. 0.846 would tell us that we have a moderate negative relationship. And again, the values that we looked at on the last slide work for a data set with approximately 20 values. For more data values or less data values, it changes those cutoff points a little bit. But this one would be a moderate negative relationship. In this one, we have a positive relationship because the data points are going up as we go from left to right. This one looks a little bit stronger than the one over here. This fits a straight line pattern better. So we would expect the R value to be fairly close to 1. The R value for this one is actually 0.95. So we would call this a strong positive relationship. Here's another one. In this one, you can kind of see that the data is going down from left to right somewhat, but this would be a very weak relationship, or maybe no relationship. So the R value for this one is actually negative 0.35. In this one, we can see that the data is trending up from left to right. Again, this is not a very strong relation, but it's a stronger one than the last one we looked at. The R value for this one turns out to be 0.635. So we would call this a weak positive relation. And finally, we have this one. Now this one, we do have something very close to a straight line, and it's going down from left to right. So this one is going to have a negative R value, and it should be close to negative 1. This one turns out to be negative 0.996. So this one we would call a strong negative relation, actually a very strong negative relation.
Now we're going to look at section 4.4 about contingency tables. The objectives for this section are first to define the elements of a contingency table, and then to construct contingency tables. So first, let's define elements of contingency tables. A contingency table, or a two-way frequency table, is a table in which frequencies correspond to two variables. One variable is used to categorize rows, called the row variable, and a second variable is used to categorize columns, the column variable. Each box inside the table is called a cell. Here's an example of a contingency table. A U.S. News and World Report article about polls stated, "On sensitive issues, people tend to give acceptable rather than honest responses. Their answers may depend on the gender or race of the interviewer." To support that claim, data were provided for an Eagleton Institute poll in which surveyed men were asked if they agreed with this statement. Abortion is a private matter that should be left to the woman to decide without government intervention. The contingency table below summarizes the results of the poll. So the information we have is broken up by the subjects and whether they agreed or disagreed with the statement, and also by the gender of the interviewer, whether the interviewer was a man or a woman. So the contingency table has two variables, and those are the same as what's in the rows and the columns. So one variable is the response of the man who was being interviewed. The other variable is the gender of the interviewer. So for each one we have two values for the variable. So gender of interviewer, we have either man or woman, and for the response to the question,
we have either agree or disagree. Those are our values. So for example, this 560 here is the number of men who agreed with the statement when they were interviewed by a man. The 308 is the number of men who agreed with the statement who were interviewed by a woman, and so on. The second objective here is to construct contingency tables, and how we do this depends on the form that our data is in. So first we can construct contingency tables from data that's already been summarized. Sometimes we just get a list of numbers of how many subjects were in each different combination of categories. So if we have a summary like that, then what we need to do is identify what the two variables are, and then identify the possible values for each one of those variables. Once we've identified those variable values, we'll use those as our row headers and our column headers in the table. And then finally we just fill in the cells of the table with the numbers from the data summary that we had. So here's an example. In an experiment to test the effectiveness on echinacea on preventing the common cold, subjects were given either a 20% echinacea extract, a 60% echinacea extract, or a placebo. Subjects were then observed and identified as becoming infected with a cold or not becoming infected. Among subjects given the 20% extract, 48 became infected while 4 did not. Among subjects given the 60% extract, 42 became infected while 10 did not, and among those given a placebo, 88 became infected while 15 did not. Create a contingency table showing the results of this experiment. As you can see, it's kind of difficult to tell the results when they're listed out in a paragraph form like this. Most people find it a little bit easier to interpret results like this if they're given in a table. So that's where our contingency tables come from. So the first thing we want to do is identify our variables and then identify the possible values for each variable. So our two variables are, first of all, the treatment given, whether it was some form of an echinacea extract or a placebo. The possible values for this are either a 20% echinacea extract, a 60% extract, or a placebo. Then our second variable is whether the subjects became infected with a cold or not. So the two possible values for that are either they became infected or they didn't become infected. Okay, so to construct our table, we've got our variables and the values, and we can choose either variable as the row variable, and then the other one will just be the column variable. So if we choose the infection status as the row variable, then our table is going to look like this. So for our row headers, we've got the two values for that variable, so infected and non-infected. For our column headers, we've got the three values for the treatment, so either the 20% extract, the 60% extract, or the placebo. So now we've got our headers done, and now we just need to fill in the cells of the table. So here's the information that we were given with the actual numbers. So we're just going to put these in the appropriate places in the table. Here's the table that we started with. So we can just go through this, and here we've got the subjects that were given the 20% extract, so those numbers are going to go in this column. So 48 became infected, 4 didn't. So we're going to have a 48 here and a 4 here. And then we go over to the 60% extract and we get 42 and 10, and for the placebo we've got 88 and 15. So here's the table with all the numbers in it. If we want to give ourselves a little bit of extra information, then we can do row totals and column totals as well. Now the other thing that we might need to do is to construct a contingency table from raw data. This is a little bit harder, especially if the data set is very large. So if the data set is pretty small, then we can do this by hand, just by counting up how many observations are in each combination of categories. Otherwise, we want to use software, either some type of statistical software. We're going to use StatCrunch in an example. Or if you have the information in Microsoft Excel, you can do pivot tables if you know how to do that. So we still have to start out by identifying the two variables and the values for each one. And then again, we use those variable values as row and column headers. Here's the example we're going to look at. A study of 4th, 5th, and 6th graders in Michigan looked at which factors children consider most important in determining popularity. The children filled out a questionnaire and were asked to rank 4 factors: grades, looks, sports, and money, in order of importance in determining popularity. So we're going to use StatCrunch to create a contingency table for the two variables from this study, grade level and the factor ranked first for popularity. So this data set is in StatCrunch already, so I've signed into StatCrunch. This data set is in our class group, so if you'd like to follow along, you can go to my StatCrunch and log in and go to our class group. So I'm going to our class group. Here it is right at the top, ACC Stats Fall 14. So I'm just clicking on the thumbnail. That takes me to the group, and notice it has a data sets preview down here, but if we want to see all the data sets for our group, we can just click on the 19 data sets up here. Just click on the word data sets, and that will show us the complete list of data sets for our group. And I'm going to scroll down here to the Popular Kids study, and this has a more complete description of the subjects and the different questions that were on the questionnaire that the kids filled out. So let's just look at the data set. Okay, here it is. So we've got all these demographics for the kids, whether they're in an urban or a rural setting, which elementary school they were from, their goals in terms of whether they wanted to be good at sports or popular or get good grades. And here is one of the variables we're interested in, which factor they ranked first as being more important for popularity: grades, sports, looks, or money. So we want to do a contingency table that uses that variable versus what grade the child was in, so grade 4, 5, or 6. In order to do that, we're going to press the Stat button here. We want to go to Tables, and we're doing a contingency table. And this one we're using raw data, so we'll tell it with data. Okay, a dialog box comes up and it's going to ask us which variable we want to use as the row variable and which one as the column variable. So let's just pick grade as our row variable. It really doesn't matter, we could pick either one as our row variable and then the other one as the column variable. Our second variable was which factor the child ranked first, so we'll choose that one. Now if we wanted to filter our data before we did the contingency table, or if we wanted to group it by some other factors, we could use these two tools, but we're not going to do that here. So I'm going to click on Next at the bottom. If we wanted relative frequencies in addition to our regular frequencies, we could click here where it says % of total. That would give us a relative frequency for each cell in the table. Or if we wanted to know what % a certain cell had in its own row, we could click row %. If we wanted to know a % in each column, then we could click column %. But right now we're just looking for frequencies, so we're not going to check any of those boxes. And this procedure will automatically do a hypothesis test unless you tell it not to. So let's uncheck this box because we're not doing hypothesis testing yet. So now down at the bottom you can click on Calculate. Depending on which version of StatCrunch you're using, this may say Compute instead of Calculate. And here we have our contingency table. Notice that it automatically categorized our variables. It gave us all the different values that came up for grade and for factor ranked first. Now if we want to save this contingency table, we can either save it to our StatCrunch account, you can copy it and paste it into a document, or you can print it. So what I'm going to do is save it to my StatCrunch account. So here it says export to my results. That's what I want to do. And I'm going to name this so that I know where it came from. So I'm naming it Popular Kids Contingency Table. I don't want to share with everyone in the StatCrunch world, but I do want to share it with our group. So under Share with Groups right here, I'm highlighting ACC Stats Fall 14. And if I want to write some notes to myself so that I know more about this, I could put that in here. Tags are to make it easier to search for this. So now I'm going to click on Export at the bottom. And that saved it to my StatCrunch account, and the results should show up in our class group. So if we go back to our class group that we had pulled up, now this has the data sets. I want to go back to the actual group. So I'm just going to go over here and click on the thumbnail again. And notice now up here it says 19 data sets, and it also says 1 result. So if I want to look at all the results for our class, I would click there, and we only have one right now, which is this table. If I want to see the table closer up, I can just click on it or click on the title, and it brings it up. Now one other thing we can see by looking at this table is we can get an idea of how the two variables are related to each other. So we have the children split out by what grade they're in, and then we have how many in each grade chose each one of these factors as being the most important for popularity. And notice that money was the factor that was picked the least in any grade. But as far as which other ones were picked, it's different depending on which grade they were in. For example, for the 4th graders, the factor they picked the most was looks. Whereas for the 5th grader, the factor they picked the most was sports. And if we look through the columns here, notice that for grades, the grade level that picked this one the most times was the 5th graders. For looks, the grade that picked this one the most times was the 6th graders. And for sports, the one that picked this one the most was also the 6th graders. So we can see there is a difference between the 4th, 5th, and 6th graders as to which one of these factors they might think is the most important for popularity.
Our last section in chapters 2 and 4 is about graphical misrepresentations of data. The objective here is to describe what can make a graph misleading or deceptive. One of the major things that I want you to take from this course is to be, at the very least, an informed consumer. To not be taken in by misleading graphs or statistics that are claimed but aren't backed up with real data or statistically valid studies. So it's important to recognize misleading and deceptive graphs and identify exactly how they are misleading or deceptive. So some graphs simply contain errors, but others are technically correct but misleading or deceptive due to specific design elements. So some of the design elements that can make them misleading or deceptive are using a non-zero axis, having two graphs that have different scales, and using pictographs that use two or three-dimensional figures inappropriately. So a non-zero axis means that one or both of the axes begin at some value other than 0, so that the differences are exaggerated. So here's a bar graph that gives the percent of those who agreed with a court decision to have a feeding tube removed. And this is split up between political parties. So we have Democrats, Republicans, and Independents. And just looking at this graph, it looks like the Democrats, like a much higher percentage of the Democrats, agreed with the court's decision than Republicans or Independents. But if you actually look at the numbers, this is only 62% compared to 54% for both Republicans and Independents. And notice that the differences between those percentages are very much exaggerated because this vertical axis starts at 53 instead of starting at 0. So this would be a case of a non-zero axis being used to exaggerate differences between values. If we redraw this graph using a zero axis, so here our vertical axis starts at 0 instead of starting at 53, notice that here this graph looks a lot different, and the differences between the percentages are not nearly as exaggerated as they were in the graph on the left side. Using graphs with different scales is another way to give a misleading picture of two sets of data. So here we have two graphs, one for Extremo weight loss pills that shows the total weight loss in pounds of their customers. The other graph is for other weight loss products. So looking at the two graphs, it appears that much more weight was lost with Extremo weight loss pills than with other weight loss products. But if you actually look at the numbers on the scales of the graph, the one on the left, the frequency, the vertical axis only goes up to 30, while the one on the right, the vertical axis goes up to 60. So the one on the left is exaggerating the frequencies of customers who lost weight compared to the other graph. Also, if you notice, the horizontal scales are quite a bit different. The one on the left goes up by tens, so the top value here is 50, but the one on the right goes up to 100. So the top weight loss for the Extremo weight loss pills was somewhere between 35 and 45 pounds, while the top weight loss for other weight loss products was somewhere between 90 and 110 pounds. So that's a lot of difference. Now, another way that graphs can be misleading is if they use pictographs. And you actually see this quite a bit. Graphs, some of them use three-dimensional objects like money bags or stacks of coins or army tanks, people, etc. to show data. The drawings can create false impressions that distort the data. And one of the ways that this is done is by using either two or three-dimensional figures instead of one-dimensional figures to represent data. Now, if you double each side of a square, the area doesn't just double, it increases by a factor of 4. If you double each side of a cube, the volume doesn't just double, it increases by a factor of 8. So especially using three-dimensional pictures to represent one-dimensional data really exaggerates the differences. Here's an example. The picture that we see here is misleading because it depicts one-dimensional data with three-dimensional boxes. So the last box is actually 64 times as large as the first box, but the income figure is only 4 times as large. So this is definitely exaggerating the difference between the income for those with no high school diploma, which is 18,734, and the income for those with an advanced degree, which is 74,602. But if you just look at the sizes of the boxes, this last box on the right looks huge compared to this first box on the left side. Now let's look at this with just a regular bar graph instead of using the pictograph. And notice here, obviously the income for those with an advanced degree is still quite a bit more than for those with no high school diploma, but the differences are not so exaggerated. This is a much more fair way to represent this data.